Welcome to The Explainer. If you're studying computer science or just taking your very first steps into the world of compilers, it is so incredibly easy to feel totally overwhelmed by all the heavy terminology. Seriously, it's a lot. But today, we're going to completely drop that academic pressure. Instead, we'll take a calm, step-by-step journey into what I think is one of the absolute most elegant concepts in all of computer science: how we translate human-readable patterns into a logic that a machine can actually execute. Let's get into it. So, here's a question for you. How exactly does a computer learn to read? As humans, we just glance at a page, and our brains instantly group letters into words and words into sentences without even trying. But a computer? A computer just sees this relentless, never-ending stream of individual characters. It literally has zero innate concept of a word. So to build a compiler, which is basically a program that translates our code into machine language, we first have to teach the computer how to group those isolated characters into a meaningful vocabulary. To really appreciate why this is such a massive challenge, I want you to imagine reading a giant 500-page novel where spaces don't exist at all, just a wall of letters. The cognitive load would be absolutely exhausting, right? You'd constantly have to backtrack just to figure out where one word ends and the next one begins. Well, historically, this wasn't just some abstract thought experiment. In early programming languages, like Fortran, white space simply didn't matter. A compiler literally couldn't rely on spaces to act as simple dividers between words.
Take this classic Fortran snippet. The string do99i, that could be the start of a do loop, or, depending on the context, it could just be a completely custom variable named do99i. If the scanner sees a comma later on down the line, okay, it's a loop. But if it sees a decimal point, like that 1.10 right there, it's a variable assignment. The scanner basically has to guess, read ahead, and sometimes actually backtrack just to understand the basic vocabulary of the code. So clearly, we need a bulletproof way to define what a valid word or token looks like.
Part 1. Patterns, regular expressions. So how do we actually define those bulletproof rules? We use something called regular expressions. They act as this really convenient, super elegant notation for specifying lexeme patterns using just a few simple rules, mainly union, concatenation, and closure. Now, I know terms like closure sound like really heavy math, but I promise, they're really just a beautiful shorthand recipe. Union simply means this or that. Concatenation means this and then that. And closure, that just means repeat this 0 or more times. That's the whole shebang. For example, take this wonderfully intuitive little formula. This right here is basically the universal pattern for a variable name, or an identifier, in almost every programming language out there. It simply says, start with a letter. That's the first part. Then, inside the parentheses, we have a letter or a digit. And that little star at the very end, that is our closure. It means allow any combination of letters or numbers as many times as you want. With just a few basic symbols, we've instantly defined an infinite number of possible variable names. Kind of mind-blowing when you think about it.
Part 2. Machines, finite automata.
Now, a pattern written on a piece of paper doesn't actually do anything on its own, right? We have to build a conceptual machine to check it. And this brings us to finite automata. Let's totally remove the intimidation factor from that terminology. An automata is really just an abstract mathematical machine. Think of it as a very precise flowchart or a step-by-step checklist. It looks at exactly one character of text, follows an arrow to a new state based on what that character is, and repeats the process. If it successfully reaches the very end of the flowchart when the word ends, boom, the computer accepts the word. Notice the visual flow of these machines. What we're looking at is a non-deterministic finite automaton, or an NFA for short. See those little Greek epsilon symbols on the arrows? Those represent empty transitions. Basically, it means the machine can casually glide from one state to another without even reading a single character. It is incredibly forgiving. It essentially makes guesses as it walks along the path, branching out to explore multiple possibilities all at once. It always helps to see these concepts side by side. On one hand, we have the NFA, which is non-deterministic. It's beautifully flexible, allowing for those magical, empty input guesses. On the other hand, we have the DFA, the deterministic finite automaton. The DFA is strict, it's concrete. For every single state and every possible character, there is exactly one clear, predictable path. No guessing allowed whatsoever. Honestly, they are just two sides of the exact same coin. The NFA is super easy for us humans to design based on our regular expressions, but the DFA is what a computer practically needs to execute code quickly and predictably. Part 3. The bridge, conversion.
Now we enter this really beautiful translation phase where we actually bridge the gap between our human-friendly regular expression and our machine-friendly DFA. The whole process happens in 3 highly logical steps. First, we parse the regular expression into its basic parts. Second, we build an NFA using simple building blocks. This is actually an algorithm known as the Thompson Construction. And third, we convert that highly flexible NFA into a rock-solid concrete DFA. You absolutely do not need to memorize the algorithmic proofs right now, just focus on the elegance of the pipeline itself.
I love how visual and tactile step 2 really is. To build a complex NFA, we literally just snap smaller, basic machines together. If you want to connect machine R and machine S, you just draw an empty epsilon transition from the end of R straight to the beginning of S. It is exactly like snapping building blocks together. You take these tiny, completely understandable pieces and you just chain them into a much larger working model. And this brilliantly illustrates step 3, which is called subset construction. Now, converting a guessing NFA into a strict DFA might sound completely impossible, but the logic is incredibly clever. We simply bundle together all the possible states the NFA could be guessing at any given moment, and we just draw a circle around them. That entire bundle becomes a single, perfectly clear state in our new DFA. Notice how states 1, 2, and 6 from the top NFA get bundled into one definitive starting state at the bottom. All the ambiguity vanishes, leaving a single, perfectly clear path for the computer to actually follow.
Part 4. A peaceful takeaway.
As we wrap up our explainer today, I want you to intentionally drop any remaining pressure you might feel about having to memorize compiler design right this second. The math and the algorithms, they're just tools. In fact, this quote from one of our source texts perfectly captures the real heart of the matter. The study of compilers is mainly a study of how we design the right mathematical models, balancing generality and power against simplicity. You see, computer science isn't just about raw calculation. It's really about finding harmony. We took a messy, basically infinite human concept like text patterns, modeled it with simple expressions, visualized it with flexible graphs, and ultimately condensed the whole thing into a strict, perfectly efficient machine logic.
I'll leave you with this lingering thought to chew on. Isn't it incredibly beautiful how human language perfectly translates into machine logic? The very tools that allow a computer to read our code are born from this deeply creative, almost architectural process. So the next time you type a simple variable name into your code, just take a second to appreciate the silent, invisible machines snapping together behind the screen to read it. Thank you so much for joining me on this explainer, and as always, keep learning.